how can we go from animal studies to human studies? Well, some of you might have heard about a drug that's called Metformin. So I have 2 pills of Metformin. That's all diabetic patients need in order to control their diabetes for a long while. I hope you can see it now. And people who take this drug, if they are not diabetes, it will prevent diabetes. But, and by the way, when you give it to animals, they live longer and they live healthier. So we know that from the biology of aging. But it's a drug that is safe, has been 60 years in use, is generic, so it's cheap, but it has curious side effects. One of the side effects is that people with diabetes, if they're on metformin as compared to other drugs, they have 30% less cardiovascular disease. If they're on metformin, they have 30% less cancer. If they're on metformin, whether they are diabetics or not, they have less cognitive decline and less Alzheimer. And this is the data that really got to me. This is a study from the UK where they took 200,000 people, half of them are controlled in the red and black line, and watched their mortality. Now, the blue line is for a drug called sulfonylurea. The people with diabetes on sulfonylurea had higher mortality. We know that people with diabetes have higher mortality. But in the green line are the people with metformin. And the people who use metformin, it's not only that they had less mortality than the people with diabetes who are treated with other drugs, but they had less mortality than the control, significantly less mortality than the control. They had diabetes, they were more sick to begin with, and they were more obese to begin with, and yet they survived later. So that shows us that metformin can be really a great tool in order to target aging. Why am I saying that metformin is a tool? Well, first of all, we have to do the study and we have to do it right. And with the help of the American Federation of Aging Research, we launched a study that's called TAME, Targeting Aging with Metformin. And in this study, we're going to select elderly people and randomize them. 3,000 people, we randomize them to placebo and control. And what we're going to look at is the onset of diseases. Which diseases? We don't care. We're agnostic to the disease. Every disease will get a point. It's all about aging. So we are going to look at cardiovascular disease and diabetes and cancer and dementia and cognitive decline and death. And everybody gets a point. But we're going to show how metformin changes this rate of aging. And we're going to have some other secondary outcomes to really depict the functional decline of aging. It reminds me this couple in Palm Springs, and the elderly couple, and the woman turns to the husband and says, honey, why don't we go upstairs and make love? And the husband looks at her and says, sweetie, I cannot do both. Those are kind of the functional thing that we want to take care of. So the second thing that is important, beside doing the study, is to work with the FDA, because what we don't have as indication to target the diseases of aging, and we're doing that. We're sitting with the FDA, and we have a plan that at the end of the study, they'll tell us, yeah, we're going to approve that. If they don't approve that, the healthcare providers are not going to pay for the drug. It's not a problem with metformin, it's really cheap. But we need to have an indication for aging. If we have an indication for aging, how life is going to change in the next decade? Well, first of all, if there's an FDA approval, then pharmaceuticals are going to jump in and develop better and better drugs, next generation, that could be even used in combination, and our Healthspan will increase and increase. just like pharmaceuticals have been successful in doing it for cholesterol lowering or for blood pressure monitoring. The second thing is there is a longevity dividend. My colleagues have shown that even a modest increase in Healthspan, like by over 2 years, will result in $7 trillion of saving by the year 2050.
The second thing that uniformly extends life across this is a drug called Rapamycin, which is kind of like my favorite drug in the whole world. I mean, meaning it's like, I think it's the most important drug in terms of this space. Not necessarily because it's a drug that we'll all be taking, though I do believe that is the case, but more importantly because of what it's taught us about the nutrient sensing pathway and its target, which is this protein called TOR, the target of rapamycin, or mTOR, as you've probably heard of it, is mechanistic target of rapamycin. And rapamycin inhibits that. Now, it's a bit complicated because there's two variants of it. There's something called mTOR complex 1 and mTOR complex 2. And if you take rapamycin day in and day out every day, which, for example, transplant patients do, it's an immune suppressant. That doesn't seem to really extend lifespan. But if you take it in a pulsatile way, you selectively get this mTORC1 inhibition without the mTORC2 inhibition. That seems to produce longevity big time.
And how does that work? How would you take it selectively?
Well, this is sort of one of my main clinical interests because I obviously I'm waiting for the day when I can start taking it and ultimately, feel that it's safe enough that I could give it to patients. If I'm extrapolating from all of the best data out there, so that's looking at the work that's come out of a guy named David Sabatini's lab. David's a guy at MIT. He's a professor. He's actually the guy that when he was a medical student doing his PhD in 1994, actually discovered how rapamycin works in mammals. He's actually the guy that coined mechanistic target of rapamycin, mTORC, as a name. And so now, whatever we are, almost 25 years later, he's still running the powerhouse lab that understands it. So if you look at all of the literature that's coming out of their lab, coupled with a guy named Matt Kaberlin at the University of Washington, who's doing rapamycin studies in dogs, along with the work done by someone named Joan Manick, who was at the time at Novartis, is now at a company called Restore Bio, and a few other people, my intuition is that somewhere between 2 to 6 milligrams every 5 to 7 days is probably the sweet spot. But, am I confident enough in that to say that we should all be taking it? Not yet. There's a couple things that I want to be able to measure before we do that. But, in the animal data, this stuff's remarkable. If you look at Matt Kaberlin's dog data, it's remarkable.
Like what are they doing with it?
Well, so you own a dog, you know this, right? I mean, if you look at outside of euthanasia or accidents, how do dogs die? They basically die of cancer and heart, and they get dilated cardiomyopathy. So it's a different type of heart disease than humans get. They don't get atherosclerotic disease; they get heart failure. Their hearts just get too big, and their ejection fraction, which is the amount of blood, the percentage of blood that leaves the ventricular chamber with every contraction, as that number goes down, bad things happen. Now, to put that in perspective, you and I sitting here, a couple of normal fit dudes, we probably have a resting ejection fraction of 60%. And if we went out there and killed it and worked out as hard as we could, at peak, we might get that up to 85% ejection fraction. So once the ejection fraction gets below 30%, a person starts to become very symptomatic. Well, Matt took these dogs that had low ejection fractions to begin with, and I forget what the exact number was, but it might have been below 40% or below 30%, put them on rapamycin for 12 weeks, and in just 12 weeks saw an absolute 10% improvement. So that means that's not going from 30 to 33, that's going from 30 to 40% EF improvement. In other words, it's hard to measure an effect in 12 weeks of a drug. And certainly you're not going to be able to measure a longevity impact over that. So much of the study that's being done with this is looking at surrogate markers that we assume would portend longevity. So Matt's work focusing on the ejection fraction, Manick's work was focused on immune response, which again so this was the turning point for me. This was December of 2014 was when everything in my professional world shifted in terms of my interest towards rapamycin is the thing I want to know everything about.
So this is our first molecule that we are putting in humans probably next month. We're just waiting on approval. This is called NMN, and its full name is a mouthful. It's nicotinamide mononucleotide, but essentially it's the immediate precursor molecule to NAD in the body. So we make it all the time, but just not a lot of it, and less as we get older. You can boost the levels of NAD up by exercising and dieting, but here is a way to do it artificially. So I'm going to show you a bit of data. We've done a lot of experiments, and the field has shown that NMN is very effective at mimicking caloric restriction. We now know it even makes mice live longer, just by putting it in their food or in their water. And it's a very safe molecule because it's naturally occurring. What I want to show you today is unpublished work that addresses the problem of frailty. And frailty is one of the biggest problems because it also leads to all these other diseases here. And the main problem is that as we lose our ability to exercise, our bodies also become increasingly less responsive to exercise. Okay? Even if you put an elderly person on a treadmill, they're not going to become a marathon runner. And we were wondering why. And not only that, why? The second question is, why can't you take a person here, poor Burt Reynolds, can we make Burt go back to here? Wouldn't that be something? And then he could then get back on a treadmill and reverse that cycle. Now that's what we're aiming for. We can actually do this in mice quite easily. We put this NMN molecule in their water, they drank it for a month, and then we put them on a treadmill. Now apologies for black mice on black treadmills, but I think you can tell which mouse has been drinking the NMN. Actually, the mouse on the bottom gave up, and someone once joked that that mouse is smarter than the other one. But actually, when you test them, the mouse on the left is also smarter. So these are the tablets that we're going to be using in our first clinical trial. The first trial, please don't ask to sign up for the trial. I get emails every day. Eventually, there will be bigger trials. This one's just going to be 30 people, volunteers, to see if it's safe. We're not expecting any issues, so we'll move rapidly into tests of endurance, tests of strength, tests of bodily functions, inflammation, and blood sugar. And this will give us a signal whether or not we're really mimicking caloric restriction. We're aiming to use this in a number of ways. We want to do a clinical trial here in Australia, treating metabolic diseases, such as mitochondrial diseases, where there's not enough energy in the cells. This is very good at boosting energy. It's also a very good cure for jet lag, if you're wondering.
No one knew if these accumulated senescent cells that collect as we age were good for you, bad for you, or neither. And so what we did, in collaboration with both Jan and Judy, is we took their multiple strains of mice and did experiments both in natural aging and in models of disease where we could eliminate these cells and ask the question, what happens? This is what happens. So these guys are siblings, born within seconds of each other from the same mom. And to give you a sense of age, these mice are the equivalent of 70-year-old people. Or if you were a mouse, that's what you'd be when you were 70. Now, this guy on the left is blind, osteoporotic, and frail, has kidney dysfunction, cardiac dysfunction, generally a sad case. Its sibling on the right, on a population basis, has a median increase in lifespan of about 35%. We think that's the boring result. The much cooler result is this animal has a profound extension of a period in its life we call health span. This is the period in which that animal lives free of these diseases of aging. And what we're doing at Unity is we're making drugs that will do that. Now, since we started this work 5.5 years ago, we have identified 21 different phenotypes that happen when we eliminate senescent cells either from naturally aged mice, progeroid mice, or animal models of disease.